Uh, Good. So what we'll do today is something very likely things that you've all seen before. So generally speaking, when you have a point in a 2D space and 3D space, which is what you're probably focused on, okay, we'll begin from there. We'll begin with what you know. Okay, if you have a point in a 2D space, how do you represent that point? Yeah, but algebraically? Coordinates. Okay, how would I write it? Two numbers. Okay, so we'll write something like this. Okay, so x1 and x2, and these are like the two coordinates. You probably usually see it as x and y, but for now, okay, uh, right. Many of you may, I mean, you've probably seen it as xy or xyz, okay, but we are kind of trying to unlearn some of those things too, okay. Not because it is wrong, but there's a more comprehensive way to do things, okay. So we'll just write them as x1 and x2. x1 and x2 can be numbers, they can be real numbers, they can be complex numbers, okay, but we are trying to keep things simple here. So while a lot of what we say will apply to complex numbers too, in this class we'll focus on real numbers. Okay, so unless I say something specifically, x1 and x2 are two real numbers. Okay, and this is how you would write a point in 2D space. Okay, and the idea here is that number one, x1 and x2 cannot be interchanged. There is an ordering to them. Okay, you can't flip them around. It's not the same thing. If you flip up x1 and x2, it's not the same point anymore. Okay, and the way you normally think of this point geometrically is this: you have a 2D coordinate system. You have a 2D coordinate system. Okay, and I'm thinking of these as if they were positive, because we all like positive numbers. It's something built into us, but really it does not have to be positive or negative or zero. Anything is okay. But what you would do is you would move x units along the first axis. I know that I'm just calling it the first axis, not the x-axis anymore. Okay, I move x units. The units are not so important right now. I move x1 units along the first coordinate, and then I move x2 units along the second coordinate. Okay, and the point I end up with, okay, that's the point x1, x2. Okay, and we'll give this point a name so I don't have to keep writing it. Okay, the name I give it is a, so I'll always write a little bar underneath it like this. Okay, that tells us that it's not just a number, but it's a vector. Okay, you guys probably can come here, like, rather than sit in the back. Like, the three of you can probably come here. So okay, so this point V. Okay, so this is the point V, and this everyone is familiar with. Okay, so what we do is right now we just extend what you know. We join the origin. Okay, we join the origin to this point V. Okay, and this blue line. Okay, so this blue line the blue line with an arrow on at its tip, that's a vector. Okay, that's going to be this vector x1, x2. Right? It may be a little different from what you do in physics. Okay, because in physics, when you study magnetism and so on, you're actually thinking of a vector field. Okay, there are vectors that are associated with every point in the space, and every point in the space has some vector with it. So that's not what we are doing. Okay, So a vector for us is simply this. Okay, you mark this point x1, x2 in your coordinate system. The line, so the vector is a directed arrow. Okay, there's an arrow only on one side. It starts from the origin. The tail of the vector is always at the origin, always fixed at the origin. The tip of the vector is at the point at the origin. Okay, so this is always going to be our vector. Okay, so any questions? Yeah. 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 The origin is always the 0 point. Yeah. We don't have a homework yet, so let's defer that question for a moment. Okay. Yeah. Those are not vectors. We'll come to that. Yeah. Okay, so right, so that is a longer answer which will not completely do today, but one convention that we will follow, and the text is a little inconsistent about that, because in the initial chapters, there are sentences that seem to indicate that this and this, or like I think you're saying that writing vectors horizontally or vertically. They're not exactly the same thing, and we do want to distinguish between these two. Okay, and we have a slightly it's common across most people. Only column vectors get names. Okay, so when you write a vector, you always mean a column vector. Okay, if you write V, if I tell you V is a vector, V is some sort of a column vector like this. Okay, it's a arrangement of numbers one below another. Okay, there's only one column. Okay, there's a single column and numbers are arranged one below another. Okay, and that's a vector. Whenever only column vectors get names, if I want to write this vector, I'll call this V transpose. Okay, so if I want to make a column into a row, I want to write a column horizontally as a row, I'll always call it a transpose. Okay, so if I wanted to write x1, x2 horizontally, if I wanted to arrange them horizontally as I was wanted, I would call it V transpose. Okay. So if that was that T as a sort of right. Right. So who hasn't seen a transpose before? Okay. Okay, so here is what it is. Like a transpose simply makes a column arrangement into a row arrangement. It doesn't change the order. You don't mess with the order. Okay, we read top to bottom, left to right. Okay, we are going to read top to bottom, left to right, but the order doesn't change. X1 is the first element, X2 is the second element, same story. Okay, and to denote it, we just write this little t on top. Okay, now you could do this with vectors with 3 coordinates, 4 coordinates, any number of coordinates. Okay, that is one big departure. Like in physics, typically you think of real things, so usually 2, 3, or 4 coordinates, or a little more if you want to do something a little more advanced. In our classes, we begin with, for the applications that we have, we think of vectors as measurements of something. Like, so for example, like there are 30 students in the class, there may be like quiz one scores for all of you, okay, and I arrange it like a vector. Okay, so we often arrange data in the form of vectors. Okay, so we measure something with many examples. Rows are usually examples. So examples in the sense like every row corresponds to one of you. Okay, and this vector is the measurement of some attribute, okay, or some feature. And in this case, like in what I told you, it may be quiz scores, for example. Okay, so what you would have is a vector with length 30 or 31, however many students are there in the class. Okay, does that make sense? Right. So it means that fundamentally, like we are not going to be thinking just in 2 or 3 dimensions. Okay, so it also means that so far you have seen many of these things geometrically, and today I'll be talking geometrically too, just to get a hook from where you were in the past. But we are going to actually de-emphasize geometry as we go along. Okay, so with vectors, you can do a few things. You can add 2 vectors. Okay, and let us say v is this vector. Let's have another vector z, and let's say that the coordinates of z are z1 and z2. Okay. Oh, that is a cursive z. Like, is that unfamiliar to most of you? Okay. I'll try to write like a.
Is that like some sort of delta? Oh, wait, never mind.
Right, I'll write, yeah, the Z that I wrote is faster for me to write, but that's, I guess, the cursive Z. But the point is not to worry about the cursive. It's not a handwriting class. Okay, so we'll stick to whatever you guys want. Okay, so let's take another vector Z, and Z has the same number of coordinates as V. Okay, when you have 2 vectors with the same number of coordinates, okay, and this is very crucial, vectors with differing number of coordinates are kind of incompatible. They don't play with each other. Okay, only vectors with the same number of coordinates play with each other. Okay, and one of the things that you mentioned before, but we will learn not to say that for a few classes, you said like 2-dimensional and 3-dimensional vectors. Okay, there is, and in physics, physicists always like to say things like that. Okay, and that is very infuriating because vectors do not have dimensions. Okay, the linear spaces have dimensions. Okay, when we mean dimension, we are going to be a little more careful. Vectors by themselves do not inherently have any dimension. They have 2 coordinates or 3 coordinates. Okay, and so it will be, it's a careless usage, and once you understand what a dimension is, you'll see why people use that abuse of notation. Okay, but for now, we are consciously going to try and do this. Okay, so when we say vectors with 2 coordinates, we say vectors with 2 coordinates. Okay, or you can use the Python notation. So in Python, if you want to look at all of this, it uses the word shape. Okay, so matrices, they have a, so we use, so in math, it's common to use size. Okay, either of them is acceptable. In Python, in programming, you use shape. In your text, you'll see the size. You'll see the word size used for all of this. So this vector has size 2, 1. Okay, 2 rows, 1 column. Okay, the 1 column is kind of redundant right now because, yeah, vectors are forced to have 1 column, but it anticipates something you'll see. Okay, or as I told you, like this vector has 2 coordinates. Okay, so let us just write z as well. Let us say okay, so let us say this is z. Okay, what is v plus z? That's right. It's also a vector with 2 coordinates. And Jenny? Yeah. Okay. Okay, x1 plus z1. And what's the second coordinate? Very good. And you are Mustafa. Yeah, sorry. Like I used to be so good at names before. Sorry. Yeah. So, okay. So your sum is also a vector with the same number of coordinates. Okay, and you just add up coordinates. You add up numbers in the same position. Okay, so geometrically, how does b plus c look like? Let me just write z in a little different way because it makes it easier for me to draw. Okay, how does v plus c look like? Right. So essentially, what you do is like in the x coordinate, you're going. So this whole distance is z1, right? So what you want to do is to move z1 here. Okay, so you're the same distance you want. So when you're looking at this sum, when you're looking at this sum, let me use a different color for that. When I'm looking at this sum, so if I want to do this sum, I want the x coordinate to be x1 plus z1. Okay, when I draw z like this, z1 is the distance from the origin till this step. Okay, what I really want to do is to move this distance here. Okay, and how do I do that? I write a new, I complete the parallelogram, so to speak. Okay, so these are the moment I have two sides in a plane. Okay, two vectors in a plane, I can always complete the parallelogram. What do I mean by that? I draw a line parallel to z, but starting from the tip of, okay, it may not look
Wait,
parallel.
did you remember to draw Z2?
Hmm? No, there's no z2 yet.
Oh,
Okay, we haven't done anything with z2 yet. We are still thinking of the first coordinate. Okay, so what I draw is I draw a line parallel to z, parallel to this vector z. Okay, but starting from the tip of v. Okay, so but this looks like three sides of a parallelogram. I just complete the parallelogram. Right now, notice that this particular point, the end of the vertex of the parallelogram diagonally opposite to the origin. Okay, diagonally opposite to the origin. What is its x coordinate? Because we started this line starting from the tip of V. Okay, its x coordinate is simply x1 plus z1. Okay, the same thing happens with the y coordinate. Okay, and so what you are doing with vectors is like when you are adding vectors geometrically, how do you see it? This is just we visualize it as parallelogram, like the diagonal of the parallelogram. Okay, so when you have any two vectors v plus z, complete the parallelogram, and the sum of those two vectors is the diagonal in the parallelogram. Okay, does that make sense? Right. So this is geometrically how you want to visualize it, and we are going to draw caricatures like this because this works whether you're looking at a plane or a three-dimensional space or like any dimensional space. Okay. Of course, we can't visualize more than three-dimensional spaces. Okay. So, but something like this works. But we'll draw caricatures anyway. Okay. Does that make sense? Right. So there is another thing we like to do with vectors, the scaling of vectors. Okay. For if you have v is x1, x2, or let me draw this picture again. You're thinking of this guy v again. What is 2 times v? You can always multiply a vector by a number.
right. Well, 2 times V is basically V, but voice of line.
Right.
Low.
Right. Right. Very good. So this is a new vector where, so 2 times v multiplies every component of v by a factor of 2, and the result is like Jackson said, it's a vector whose length is 2 times. It's another vector in the same direction, but twice the length. Okay, so a vector that is alpha times v is in this. It's a vector in the same direction as v. Okay, but length is scaled by alpha. Alpha could be greater than 1, less than 1, negative, doesn't matter. Yeah. Right. We'll come to that, yeah, but they're the same. Okay. But we do not, so by convention, like we are not representing any of the transpose vectors geometrically. Like I said, like we are kind of de-emphasizing the geometry. We are just talking of geometry in the first few classes, just so it's a comfortable transition from what you know to what you will know. Okay. Yeah. So it's a column. One example. Yeah, that would be one way to think about it. Like, so when we look at matrices, it will become more clear. And when you take slices in Python, when you take slices of matrices, so you'll do it. It's actually your first 2 labs. You'll do a lot of this. You extract rows and columns from matrices. And Python has, and this you will learn in the lab a little more detail. Python has a slightly different way of approaching all of this, but all these are conventions. Okay, so in class, yeah, you can that would be completely consistent with the convention. Okay, you think of like a row vector as one example with 2 attributes. Like so, you measure this one and fix this force of Maxwell. Okay, and the column vector, it's like the Poisson scores of Maxwell and Euler. Okay, so that's the convention that we use across machine learning. Okay. Yeah. So, right. So, but also keep in mind this. These are not like fundamental things. These are just conventions. Okay. So don't give it more importance than the fact that it's just a convention to make things easier to do. Okay. Right. So we all know how to scale vectors. We all know how to add vectors. Okay. Now you can put the 2 of them together. Okay, and when you put the 2 of them together, it's called a linear combination. Okay, so a linear combination would be something like this: alpha times v plus beta times z. Okay, so you scale the first vector by alpha, you scale the second vector by beta, you get 2 new vectors and you add them. If you have 3 vectors in play, like you can have alpha 1 times x plus alpha 2 times z plus alpha 3 times w, for example. So you scale each vector by a potentially different constant and you add them up. Okay, and this is the primary object we will study in all of this course. Okay, this is called a linear combination.
Single column on 2 variables, right? Because on the quiz, I noticed there was like, a linear combination. I thought it was like, there was like a Z1 and Z2 and a ZB.
That it's what I told you, right? Like you can do it with any number of vectors. If you have z1, z2, z3, you scale each vector by a constant and you add them up. Right. In all of this, right, every component vector of your linear combination has the same number of coordinates. Okay, it is the same shape. Okay. In general, only vectors with the same shape play with each other. Vectors with different shapes cannot play with each other. Okay. Yeah.
Why the numbers would be 0?
Yeah. Yeah. In fact, like when you have a scaling, 0 times v is the 0 vector, the all 0 vector. Okay, that's completely acceptable. And your scaling can be negative, it can be 0, it can be any real number. Okay, In general, like it can be any complex number, but we're not doing complex. We are just sticking with real numbers in this class. Okay. Nothing we said. I mean, all of this is more generally applicable. Let's just keep it simple. Okay. So since we are working only with real vectors, real matrices, like we are thinking of the alpha 1, alpha 2, alpha 3 to be arbitrary real numbers. Okay. And sometimes I forget to write these little lines. And this is one of the reasons I'll write the little lines. But when you look at this linear combination, some of them are vectors, some of them are numbers. And so these little lines are to keep track of which one is a vector, which one is just a number. Okay. And if I forget, just remind me. Yeah, that's the same thing. Yeah. So the reason is like in a textbook, easier to write boldface, or when you're printing, it's easier to write boldface or something on the top. When you write it by hand, you will find that there will be cases where writing on top is very inconvenient. It gets confused with things that are written on top of the line and so on. So it's easier to write something at the bottom, but that's less confusing. Yeah, but some way to distinguish it from just real numbers, like the exact way depends on your artistic capability. No, they're real numbers. Okay, they can be integers, but they don't have to be. Okay, they're real numbers. Okay. Right, and so essentially, this linear combinations, what happens with linear combinations, how to keep track of linear combinations is all we will do in this course. Okay, it's very simple to define, but very powerful. And so in general, like how would you think of a linear combination of V and Z in our pictures? Like V is this, Z is this. Okay, then if alpha and beta, and we are thinking of the linear combination alpha V plus beta Z. Okay, now imagine both alpha and beta are 0. What do you get? 0. Okay, imagine beta is 0. What do you get? Right, and which is, if I run alpha across all possible values, okay, what are the points I get? Yeah, you get the origin, but I'm going to let, so here I'm looking at a set of linear combinations. Okay, it's a collection of linear combinations. So I'm going to plug in different values for alpha. I'm going to keep beta equal 0. I'm going to let alpha take run through every real number. Pardon? You get a what? A line. Very good. So Lewis, right? Yeah. So you get a line along alpha. Okay, so the set of points I get, it's like an infinite line in both directions. Okay, and every point on this line I can track by putting a different value for alpha and beta 0. Similarly, if I keep alpha equals 0, beta equals, I let beta run through every value, what do I get? A line like this. Right. If I only let beta take positive values, alpha is 0, beta is only positive values, what do I get? Right, so it's the part of the line starting from here and going this way, right? If I let only positive values for alpha and I set beta equals 0, this part of the line starting from the origin and going to infinity, okay, in the direction of V, okay? And if I let both alpha and beta take only positive values, only non-negative values, what do I get? Pardon? Right, so you get this region in between these two. Okay, because of the parallelogram law. Okay, so when I take alpha b is some point here, beta z is some point here. Okay, when you complete the parallelogram, okay, you're going to get something like this. We're going to get some point in between. Okay, so if I let alpha run, if I take the set of all linear combinations where alpha is non-negative, beta is non-negative, okay, I get the region between these two lines. I get the region between these two lines, so this area. Okay, these are called cones. Okay, this particular object, it's a cone. A cone is an object. A cone is a set of points, a set of vectors, where if you take any vector in the cone, okay, and scale it by a non-negative constant, you get another point in this collection. Okay, so if I take any point in this area, any point, scale it by a number, let's say 3. Okay, any non-negative number, I get another point within the cone. Okay, so cones are objects like that. Okay, so we're not worrying about the geometry, but just like the terminology that we use for something like this, it's not a quadrant, it's called a cone. Okay, but yeah, it's a quadrant. It's effectively a quadrant. Okay, so what happens when both alpha and beta can be negative? When both alpha and beta take only negative values. Right, you get this cone. Right, so this is alpha. If I include 0, I include the origin, otherwise I don't. Okay. Okay, and similarly, you can figure out what the others are. Okay. So, but if I run through all possible values of alpha and beta, what do I get? Every point on the plane. Okay. Yeah. So any questions? Right. So we'll be very, very concerned about these sets of linear combinations, how they behave, and basically keeping track of linear combinations. How do these sets of linear combinations behave? What are their properties? Those are what we are going to do in this entire course. And insights into those are very powerful. Okay. Insights into those are things that tell us, like, for example, I'm going to show you a demo when we start doing the problems. It's not something we are ready to do yet, but but the concepts behind that demo, we will understand by the time we are at the end of the course. Okay, but when you recognize people, how do you think you recognize people? When you look at faces and recognize people, right? We are all very good at it. Humans are extremely good at recognizing faces. Not so good at recognizing other species' faces, but we are very, very good at recognizing human faces. How do we do that? Do you have any guesses on like where we focus, what we do? So which part? Eyes and nose. Okay, and so this we have learned by experience and probably teaching kids, and we don't have to teach it, sort of built into us, right? Now, I'm going to show you a demo where just these concepts of linear combinations are used in all the different ways we go through the class. Will tell you the same answer. It is going to look at a bunch of faces, and it will show you in order to distinguish between the faces, where you need to look at are the eyes and the nose. Okay, the eyes, nose, this is the primary areas to look at. And the program knows nothing about human faces, okay, but it's going to figure it out anyway. Okay, so these look like an abstract thing, but they're super powerful. Okay, these notions, they're extremely powerful, and you can go very far with thinking about this. Okay, okay, these are about basic linear operations, basic linear combinations. But with vectors, we do one more thing. Okay, you may have seen more of these in physics, but here we'll only think about the dot product. Okay, so you've all seen the dot product. In physics, you see cross products. You see there is also a triple product. All of these. Okay, they're useful for dealing with vector fields, but fundamentally, from a linear algebra perspective, the dot product is fundamental. And we use a different word than the dot product. We call it an inner product. Okay, so when both of these mean the same thing. And there is actually many different ways to do it. Okay. So when you look at the dot product, let's say V is, we used x1, x2, I'll keep that. And Z is, once again, with the inner product, only vectors of the same shape can play with each other. Okay, only vectors with the same shape can play with each other. Okay, so what is V dot Z? Yeah. Oh, you don't need to copy. I'm going to give you this anyway. Okay. So, but what is V dot Z? Okay. X1 Z1 plus X2.
Oh, wait, but that V was, vector V graph is the bottom line.
Okay, yeah, thank you. Yeah, so V dot Z is X1 Z1 plus X2 Z2, and it's a simple number. Okay, so the inner product, what it does is it takes two vectors and returns a number. Okay, so actually, like with the inner product, so this is the particular form that we are all familiar with. Turns out there's more than one way of writing an inner product. Okay, what we want from the inner product are actually three properties. Okay, so more than the particular computational form, okay, we are actually interested in these things. Okay, so the inner product, it's linear in each term. Right, what does it mean? If I take v1, a vector v1 plus another vector v2, okay, and I take a dot product of this with z, okay, I get v1 dot z plus v2 dot z. It's easy to figure out from this particular form, okay, but like I said, like this need not be the only form for a product. Later on, we'll see other ways to define the products. Okay, but you want it to be linear in each term. You also want scalings. Okay, same thing with scalings. Like alpha times v, the vector alpha times v dotted with z must be just alpha times v dot z. So when you're looking at linear combinations, when you put the two of them together, if I have alpha 1 times v1 plus alpha 2 times v2 dot z, I get alpha 1 v1 dot z plus alpha 2 v2 dot z. Okay, so it's linear. So this is linearity in the first term. Exactly something similar happens if you if you do the same thing with the second argument. It is also symmetric, and this part needs, because we are dealing with real numbers.
For the Z's over there, did you get to like include the
Right.
ones and the twos?
No. There's only one z. There's only one vector z. In all of this, there's only one vector z.
Oh, because as for some of the we do again without
Right. Sometimes, yeah. Right. I think all of them have the little line now.
oh, and that one, like that one on that extra plus B.
The first example. Here? No, here these are numbers.
Down below, sorry.
Oh, here? Oh, okay. Yeah. Your eyes are better than mine. Yeah. So, right. Okay. So there's only one z here in all of this. Okay. So you need to hold one, it's linear in each term, meaning you need to hold one argument down. Okay. Here, the second argument, it's held constant. There's only one vector in the second argument. And the first one you can split linearly. Okay. If you want to split, if you have like a linear combination in both arguments, okay, you need to hold down one of the arguments, then play with the other, hold down the other one, play with the other. Okay. So we'll do that in problems. Okay. So because we are dealing with real numbers, there is also this symmetry. This is different when you look at complex numbers. You want conjugate symmetry in complex numbers, but since we are doing real numbers, we just have symmetry. Symmetry means if you have v dot z, it is the same as z dot v. Okay? And the last thing is very interesting. We will use a name for it without understanding what it means right now. I mean, without understanding why we are using that name, we'll know what the concept is. Okay, the concept is this: v dot v. If I take the dot product of a vector with itself, okay, this is always greater than or equal to 0. Okay, and in addition, it is equal to 0 okay, it is equal to 0. The dot product of a vector v with itself is equal to 0 if and only if the vector v itself is the 0 vector. Okay? So if I take v to be a non-zero vector, v dot v is something which is strictly positive. Okay? So this is called positive definite. This property, it's called a positive definite property. Why we call it that, don't worry about it now. We'll see this in more detail later. And of course, like there is the concept of orthogonality. Right? When you have v and w to be non-zero vectors, okay, you call v and w to be orthogonal if the dot product is 0. Okay. V is orthogonal to W, or V and W are orthogonal, or W is orthogonal to V, they're all the same thing. Okay? Pardon? Yeah. Perpendicular. Right. So two vectors are perpendicular. So geometrically it means perpendicular, but like I said, like we are de-emphasizing the geometry. So in this one, like you'll notice that with this dot product, two vectors will be, or if the vectors are perpendicular to each other, okay, their dot product will be 0. Okay. Actually, there is an interpretation tool with orthogonality. So it means that V and W do not contain any linear information about each other. That's what we mean by linear exclusivity to this. So here, like, so you'll see that so when we'll track information in terms of the ability to make linear combinations and so on, and when you do that, orthogonal vectors carry no information about each other. So V has no component in terms of W, and W has no component. So when you look at vectors like this, right, V and Z, like I've drawn here, they are facing in different directions, okay? But they still have some, okay, this green one and the blue one, they're still facing a little bit to here. So you could say that Z can help you tell, Z can tell a little bit about V, if not everything, okay? But when you have orthogonal vectors, okay, they will be like this. Like orthogonal vectors will look like this. Okay, they cannot tell you anything about each other. Okay, and this is right now. It's a little premature to say that I'm only answering because you mentioned that. Yeah. So, but we will see a lot about this. We spend a lot of time with this. So I'll answer the question. Okay, so we'll wrap up here. So I think, yeah, so if any of you want an extension for a quiz, you can always ask me. So I think one of the quizzes is due on Friday, and it does a little bit, right, so it does a little bit about all these dot products and anything. But if any of you want an extension for that, just let me know and I can always extend it. Yeah. Yeah. So, I only do it so that it's not mandatory, but material is not mandatory. That's the problem.
I answered those questions, but
It's nothing is mandatory. So I did the yeah. So once
I have a question about how you said vectors with different coordinates.